Welcome to Calculus in the PM. I'm your host, Mr. Shidelka. 6.2 definite integrals, Riemann sums. Riemann sums, depends who's pronouncing it. The first thing we want to take a look at, you may have seen this Greek capital letter sigma here. In math, it means add them all up, the summation. Sums are added, right? Where do you start at? K equals 1. This means you start at the first term, you plug in 1, then you go up to. Like if this was 5, you would add up terms 1 through 5, whatever they may be. If you have just n, that means indefinitely. A million, a billion, whatever, we haven't chosen. Whatever you do, now you're going to somehow generate a list of the first term, second term, third term, and so on. You add them up until you get to the ending point. If this happened to be 5, then this would have been n minus 1, 5 minus 1, 4, right? You'd add terms 1 through 5. That's this summation. Now, why do we even need this? Well, the definite integral can be thought of as adding up an infinite number of sums. Right now, we'll keep it finite. Finite meaning uncountable. So here's a definition. The definite integral as a limit of Riemann sums. Let f be the function, we're used to this now, on a closed interval from a to b. It has to be closed, so it's from 2 to 7 or something like that. For any partition p, we'll call this, so any small little portion of a to b, from 2 to 7, we'll say, let the number ck be chosen arbitrarily. Meaning it doesn't matter, just as long as it's between 2 and 7. In this subinterval, xk minus 1 to x to the k. Oh my gosh, it's getting super abstract. X value, from the starting x value to the ending x value. In that sub-small interval, smaller than 2 to 7. Now, basically, you would add up. Now, do you see the partition is approaching 0? You're trying to get the skinniest possible partition, meaning a width of 0 would be as skinny as you could make a, you're approaching a width of 0. You can't do 0 because you need an actual base, but you're imagining that your strips are getting so skinny that they're practically 0 width. The function gives the height whenever you plug in the value of, ck, 1, 2, or 3, or whatever. This is the change. So that's the small portion. We'll call it dx later in other notations. Now that's equal to the value of I, the integral. Now that's kind of tricky there, that one. We'll continue on and we'll come back to it when we need it. The existence of definite integrals. That means these integrals will give us an area under the curve. All continuous functions, has to be continuous functions, are integrable. You can do the integration. You can do the opposite of differentiation. Find the area. That is, a function, that is, if a function f is continuous, has to be continuous, on an interval from some 2 to 7 or some interval, then its definite integral over a to b exists. There's an answer to this integral problem. That's all that tells you. It has to be continuous on a closed interval. Now, let f be continuous on that interval, so 2 to 7. And let 2 to 7 be partitioned into n subintervals. Breaking it up, I could say 2 to 7. I could break that up into 5 intervals, 2 to 3, 3 to 4, and so on. Well, n intervals is even more intervals. Instead of 5, why not 10? It'd be more accurate. Why not 100? It'd be even more accurate. Why not a billion? Why not an infinite number of intervals? It'd be extremely accurate, is what we're saying. And they have equal length. The change in x, the width of each interval, is equal to, if I went from 2 to 7, I'd say 7 minus 2, that's 5, divided by the number of intervals. That'll give you the width of each interval. Now, if you think of that with arithmetic before we talk about infinite, I said from 2 to 7 on the x number line. if I said, and I don't even care what the function looks like, 1, 2, 3, 4. Now, if I said, to make it easy, divide this up into 5 intervals, right? How wide would each interval be? 1. Now, I did that because that's pretty easy. Now, if you apply this formula, do you see how this would work? What's the width of each interval if I said I want n equals 5, 5 intervals? Well, I'd say it starts at 7 minus 2, all divided by 5 intervals. That gives me a width of 1, doesn't it? What if I said I wanted 10 intervals? Well, then I'd still go 7, b minus a, 7 minus 2, final minus initial, divided by 10. Oh, I did a 0 there, so it thinks I needed it. But it's going to be half each interval, right? And it'd be more accurate. And then, like I said, why not 100 intervals? Well, they'll be really skinny and a lot more work if you were to do them by hand. Then you go beyond there. This is the idea. Why not 100? Why not 1,000 intervals? Why not 1,000,000 intervals? That'd be very accurate. Why not an infinite number of intervals? Well, the reason why not is if you have to do those by hand, you can't add an infinite number of rectangular strips area if they have a width of 0, let alone the infinite number. It just makes no sense. But calculus gets around this, eh? We'll see something, okay? Now, just back to this here. Just thinking of something here. We have this function. And I'll say from 2 to 7, I just randomly chose 2 to 7. Is this function integrable? Can I do the integration? Can I find the area? Why not? It's not continuous. And in this case, it doesn't guarantee that this area here, do you see how it goes off into sky high, right? Doesn't make sense. There are some cases where you have discontinuous intervals and you can still find the area. It just doesn't guarantee it with this, okay? Now, as long as this is a smooth curve or something like that, we're fine, even if it dips into negatives. I didn't mention that before we get to this here. Now, the definite integral. This is an operator sign. This is sort of like d by dx tells you to do differentiation, derivatives. This tells you to do the integral. And this tells you to go from the lower limit, say from 2 to 7. I keep using 2 to 7, so we stick to the same example. For some function, whatever it looks like. Maybe it looks like this. A rainbow or some portion, maybe it's quadratic or a cubic. So you would know what the function is. X squared minus 2x plus 5, something like that. dx is used, and it's like the change in x. It's that little microscopic kind of width, because we're saying we really want an infinite number of strips of 0 width. Well, that's what this dx is talking about. And just like dx and other problems when we do d by dx derivatives, the variables have to match if this is done properly. Okay? So this is the integral from a to b. The integral from, say, 2 to 7 with this function with respect to the letter x as our variable. This is just notation so far, and big ideas, like adding an infinite number of strips of 0 width. Sounds impossible, but it ain't. Now, let's do a notation example. Now, I know it's really small the way it's printed. So this is from a value of 1 all the way up to n strips, and I don't know if you can see it clearly on your paper. N is approaching infinity, an infinite number of strips. This is like my function. And I'm going to put in the first m value, m1 plus 5. Then I'm going to go to the second m value, and the third m value, and so on. Hey, this is really like my x, if you follow in this notation. The first value you plug in, the second value you plug in, and so on, okay? So what I'm thinking is, this limit here is like, I'm going to leave a space right here because I'll do the integral kind of thing. But the function, doesn't it look like it's 3 something squared minus 2 times that same something, x, plus 5? Now, that's the function. And it's pretty much an exact match, other than we use mk, m1, m2, m3, off to an infinite number. The change in x, I said, think of that as dx. That's that infinitesimal small portion. Now, we have to read for this. The interval, -2 to 4, is partitioned into however many subintervals, an infinite number eventually, of equal length. Delta x equals, well, how did they get this 6, by the way? Final minus initial. From -2 to 4. 4 minus -2 is 6. Divided by, well, an infinite number, you can't really do any arithmetic with. But as far as the integral, where does it start? -2, and it goes up to the value of 4. This means adding up an infinite number of strips of 0 width from -2 to 4 for the function 3x squared minus 2x plus 5. That'll give you the area if you know how to solve this, and eventually we will. Now this is just notation, it's not really solving anything yet. Any questions here? More theory kind of stuff then. Area under a curve, that's a definite integral. Definite meaning it has an answer. Okay? If you've got this function f of x, it's not negative, non-negative. Integrable, meaning that that implies that it's continuous. Over this closed interval from some number to another number, 2 to 7, -2 to 4. Then the area under that curve for the function from a to b, from 2 to 7, or whatever, is the integral of the function. This is just restating sort of what we've said again and again. But the integral gives an area from a to b. Sometimes you'll know how to go from first principles to do these if it's a shape like a circle. Or if it was a rectangle or a triangle. You'd know how to do it just from geometry. We're going to start with those, and then we'll figure out the calculus way to do it if you didn't know. Now, you guys aren't as familiar with circles. But, in case you don't know, that's an equation of half of a circle, the top half of the circle. If you wanted the bottom half, you'd have to put a negative sign in here. So from -2 to 2, this is really asking us, what's the area under this semicircle, okay? How do you find the area of a circle? There's pi over squared, and we'd only want half of it though, right? So we divide it by 2. The radius in this case would be 2, because 0 to 2, or 0 to -2, that's still a radius of 2. From here to here is still 2, right? So this integral is the equivalent of asking me the area of half of a circle. So half of a circle, pi, r squared in this case. Here, I'm going to put in the 2 squared. That's what this is. That's all I'm just... This is a semicircle with radius 2. Now, you don't have to figure this out to a decimal. You might just know it, but maybe you don't. What does this simplify to in terms of pi? 2 pi here, yeah. 1/2 times pi times 2 squared, 4. 2 pi. 6.28 if you wanted a decimal, but we'll keep it to 2 pi. Now, as I said, there's some things you can do on your calculator too, and I'll show you. On your TI 84 or 83, works pretty much the same. Go to your math menu. Now, if you don't see it right now, slide down or up. On my calculator, it's number 9. I think all 84s. I'm not sure about the 83s. It says function integration, F-N-I-N-T. Choose that. The newer 84s have this actual integral notation. Let's check this answer. Well, I guess, well, it doesn't matter. Where do we go from according to this? Now, I'm trying to match this, and I don't know about the 83s, the order does it. We'll have to experiment and see. Go from -2 to +2. I'm supposing, Ashton, yours doesn't show what mine shows, though, does it? Because yours didn't on differentiation.
Mine shows
It does?
it. I don't know yours.
Like, shows the S kind of? Oh, it does, okay. Differentiation, it doesn't.
No.
How about the 83s? Who has the 83? You do? Does it? Doesn't show. Maybe you'll just have to play around and try -2, 2. Okay, I'm not sure. So we're going to enter this integral here. So I'll just start this up. Oh, I did start this up. Okay, I've been wasting. So -2 up to 2, that's up there. Then we're going to put in the square root, second function square root, 4 minus sign x squared. I've got that there. Then what variable are we doing this for? X. Hit enter. I should get 6.28 something or other. Working. I do. 6.28 is 2 times pi, ain't it? So, moving along. Let's take a look at this. Hey, thanks. So, we're looking at this cosine function and the area under the graph. If a function has a non-positive, so negative area, the non-zero terms in that function, the Riemann sums, are negatives of the rectangular areas. So you're going to get like -0.7 and stuff like this, plus -0.9, whatever those areas are. If it's under the axis, under the x-axis, you're just getting negative areas. Okay? That's all that tells you. It's like in physics, when you get a negative answer, if top was going north, you'd be going south if you got negatives. That's to apply some meaning to an area if you were doing a velocity time. So if you just want the absolute value of the area under a curve, just take the opposite sign. That's what this tells you here. So that shouldn't be too, you get a negative area from some portion, it is, take the opposite side. If you got -2 as your answer, +2 is the area. Question?
What if it told you to take from like 0 to pi? What if it was half positive, half non-positive?
Yeah. So from here to here.
Yeah.
It'll add up mathematically to 0, so you have to chop that up into 2 portions. You do this area from here to here, then you do this area from here to here, and in the context of your problem, if that makes sense to make this the absolute value of the area, you would add the 2. And by symmetry, you could actually say, you know enough about sines and cosines to know that they're symmetrical, right? If you found this first area here, you could just double it and say I have the area up to here. However, sometimes you don't have that option, and you do have to break it up into two or three parts depending on the function. Another thing is in some instances, it actually makes sense to add the positives and negatives together. Because if you were talking in physics, and if this represented velocity in time, and you were asked to find the displacement, how far you've traveled from the starting point, then it would be 0. This would be going one direction up, and then coming back down, you know, that kind of thing, opposite directions. So, sometimes it does make sense. Depends on the context of the problem. What about this? If an integral function has both positive and negative values. Hey, this is what he was just asking about. What do? You take the area above the x-axis, that's the positive stuff, and you subtract the negative area. Really, you're going to add it to the area below the axis, right? And you'd add this, and so on. So it's essentially what Ashton was just asking about. If you have stuff that's both above and below, and you want to find the absolute value of the area, break it up into, in this case, 3 chunks. We'll get practice doing those. Area above, area below. It is a fact, which you can see later on when we revisit, that the area from 0 to pi for sine of x dx is 2. Now, this area is equal to 2 here. So what would this area below here by symmetry from 2 to, or pi to 2 pi would be negative 2. Absolute value, though, is just an area of 2. We'll keep this in mind. So, let's just think this stuff through here a little bit. Well, actually, I've already done the first one here. What's the actual, now when we see this, and we want area, from pi to 2 pi, sine dx. What is the area we're talking about? Now, I already wrote that one down, didn't I? That's negative, and it's from pi to, yeah. This isn't the actual area. It's asking from pi to pi. What is the sine function? It's below the axis. It's negative 2. Now, I just stated that one by symmetry, right? Let's see if it works out a bit differently. From 0 to 2 pi, it is going to add up to 0 because you have as much above, positive 2, as you do below. It'll zero out, even though if we wanted the absolute value of the area before, right? The way it's written, how about from 0 to pi halves?
How come 1 is negative?
Okay, sure. You're starting at pi, going to 2 pi, right?
Yeah. I don't reflect when it was in.
If you want to find the area, let's just see here, yeah. This is equal to the area with the sign flipped. It's confusing the way it's written here. But let's just say, if you're asked for the area, you take the opposite sign of pi to 2 pi, sine of x here. Now, so negative, if I said what is the area, we would have to take the opposite sign. But we're just straight ahead just doing pi to 2 pi. It does it say? No, it doesn't say that give all answers as areas only. Okay? Yeah, you got to be careful how it's phrased, because it is confusing.
Then how come 2 is not 0? If 1's negative, then 1.
Where did I go? 2 is 0, and I said I was talking at the same time, and I did say 0, didn't I? Yes, I did. I said then if you were asked for the area, I made a big mistake. That's all. That's the reason why. Okay, too many things going on in my head. You guys are sharp. How about 0 just by symmetry? What does it look like the pi halves here? What would you guess? That looks like the middle, right? Should be. So if the full area is 2, half of it would be 1. All right. Now 4 gets a bit tricky. What is the graph that we're talking about here? Now, normally, sine, this is our normal sine function. What does the 2 plus mean? lift it up. Okay. Now, I'm imagining this is like my center line, right? At 2. And I'm going from what? 0 to pi. Okay. What is the area at the top part? 2, right? Now what is the area of the rectangle here? It has a base of 0, a pi minus 0, so pi, and a height of 2. So 2 times pi, base times height, right? 2 pi plus 2. Now this is a pretty small drawing, but can you see what we did? The area of this rectangle here plus the area up here. Because we lifted it up 2 units. That's a doozy. How about number 5? It's from 0 to pi again, so we're only concerned with the first portion of the graph. What does the 2 in front of 2 sine x do? Stretches it, right? So if this is regular pi, this would be 2 sine x, right? What do you think happens to the area there? It should double. Because we didn't double the other dimension. We only stretched it up. We didn't stretch it left, right. So, if this was 2, this area would be 4. It doubles it. Okay. Ooh, doggy. What's number 6 all about? Sine of x minus 2 units. And then go from 2 to pi plus 2. Whoa. What happens there? What does the x minus 2 do in the bracket? It's a 6. Here's my regular function, right? Now, I'm going to do in green. What does this command me to do? To the right. Okay. So, be somewhere like this. Now this is moved over, instead of at 0, it's at 2, right? What would this midpoint be? Normally it would be pi. Pi plus 2. Okay. We're supposed to find the area from 2 till pi plus 2. Isn't this the same hump as before? Okay. So that's still 2. This is where those translations and stuff come in here. Sine of u du. Ah. Look at number 7. They changed the variable from x to u. That shouldn't matter. But negative pi to positive pi. What does that look like? And it's different if it was cosines and stuff like this. But normally we look at this half. But if we kept going this way, isn't this where negative pi would be? This is positive pi. So 2 plus negative 2? In under the axis, over the axis, right? So it should zero out. We're talking about this area. Number 7. Uh-oh. 8. What does it mean when we have x over 2 inside that function? It's working on the x. Horizontal stretch. And it stretches it by 2 times the normal amount. Just think, if you plugged into 2 pi into that equation, you'd get the answer you normally got at pi, right? Because it's cut in half. So for 8, what you'd normally get at pi, you now get at 2 pi. I'll just lift this up here. You stretched it like that. 0, pi, 2 pi. You've just stretched, you haven't changed the height though. Don't want to change 2 factors at once, it gets too confusing. So what's our answer here? We have, I see you whispering it, 4. Okay. Does that make some sense? Yeah, I think so. Nine, and we're calling it a day. What does the cosine function look like? It's really the same as the sine function, just offset by 90 or pi halves, right? So, up to pi. Now knowing this, if we had this full curve here, this would be 2 for the whole thing, right? Now, only taking half of that bell, kind of like a bell. This would be positive 1, this would be negative 1, wouldn't it? So we should have a 0 in here, and we would. If you enter these on your calculator, you could check your answers. You don't have to. But that's just doing it by picture. Now, I'm going to ask you to take a look at some questions right away, and then we'll come back to this tomorrow. Yeah. Let's just see which ones are good ones for today. I think 3, 7, 11, 15, 19. Let's see. 280 something or other. Now, what did I ask to do this time? Three, 7, 11. 3, 7, 11. By the way, 7 and 11, they're constant functions, so they're just going to give you a rectangle. A height of 5 for 7, for example. 11. 15. That's a semicircle. 19.
May I have your attention, please? There's just been a bit of concern about a smell that's coming from the basement. There's an issue with the sump pump line. It's being handled. Nothing to worry about. Thank you.
Sounded like he was on auto-tune computers.